Okay, so for our next example, let's say Sam invests $4,000 in an account that compounds interest continuously. And earns 5.5% interest. How long will it take for his money to reach $80,000? Okay. Whenever you see how long will it take, that's just another way of saying solve for time. Okay, so it says continuously compounded, so we know we're going to use A equals P times e to the power of RT. Okay, so our A will be $80,000 because that's our new amount. Okay, which means the amount we started with is our 4,000. Our interest rate is 5.5%. But we have to convert that to decimals. So that means our interest rate, just move the decimal over twice, is 0.055. Kind of highlight that a little bit. And our time, that's what we're finding out. Okay. So now we just go ahead and plug it right in. Kind of separate that a little bit. Don't need to rewrite it since it's right up there. So our A is equal to 80,000. Equal our principal, say our 4,000, times E to the R times T, so that's 0.055 times T. And now we just go through our steps. The first step is to isolate the exponential function. Okay, so we divide both sides by 4,000. Actually, I should go ahead and rewrite it since it's to avoid any confusion. So it gives us 80,000 equals 4,000 times e to the 0.055t. Divide those two by 4,000. Clean that up a little bit. Okay, these two cancel out. So that means e to the 0.055t equals 20. Now your second step, you're going to apply the natural log. So that gives us the natural log of e to the 0.055t equals the natural log of 20. Okay. Our e and natural log cancel each other out. So that leaves us with 0.055t equals natural log of 20. Okay, so we divide both sides by 0.055. T equals natural log of 20 divided by 0.055, which if you plug that into your calculator would be 54.5. Okay, so it would take 54.5 years for that $4,000 to become $80,000. So 4,000 to become 80,000. There we go. All right, so any questions on that one? All right. Everyone's done. Looks like everyone's finished. Oh, anyone's still writing? All right. Okay, so now we're going to look at exponential growth and decay. So it's pretty similar to the continuous compound interest formula, but just the letters are changed a little bit. Okay, so we'll let A equal your final amount. We'll let A sub 0 equal your starting amount, or your original amount. Compound interest, that was the P, we're making it A sub 0. T, still equal to time. But this time could be seconds, it could be days, it could be months, it could be years, it could be anything. Compound interest, it's always years. And we'll let K equal the rate of growth or the rate of decay. Okay, the rate of growth is when K is positive, and rate of decay is just K is negative. Okay, so we have that formula A equals A sub 0 times e to the kt. It's almost an identical formula, just different variables. That's exponential growth or decay. right. Now let's start with our example. Okay, so what if you have a certain bacteria declined from 100,000 to 100 in 24 hours. At this rate of decay, how many bacteria would there have been at 16 hours? Clean that up a little bit. At 16 hours from the start of the experiment. All right, so we're looking up either growth or decay. So we know we're going to use A is equal to A sub 0 e to the kt. Okay. So the first thing you have to do is identify which is which. Okay. So we know our amount is 100 because remember it started at 100,000. So A sub 0 is 100,000, which is our starting amount. And where it is now is 100, which is our final amount. Okay, so our K, we don't know what that is. They never told us. Okay, but we do know that our time is 24 hours. Okay, so the first thing we have to do is solve for K. Okay, so if we, yes.
Would it be 16 hours?
That's 16. Nope, not yet. We're actually going to, because if we did try to plug in 16 hours, we still wouldn't know K. So we'd have our A0, we had everything but the K. So we're going to use the 24 hours to solve for K, and then we're going to plug in the 16. All right, so if we solve for K, we have our A, which is 100, equals 100,000 times E to the K times 24, or 24K. Okay, so if we divide both sides by 100,000, that gives us, I'm just going to switch those around, E to the 24K equals 100 over 100,000 is just 1 over 1,000. Okay. So now if we apply natural log to both sides, that gives us natural log of E to the 24K, bless you, equals natural log of 1 over 1,000. Where our natural log and E cancel each other out. Bless you. You have 24 times K equals natural log of 1 over 1,000. Divide both sides by 24. Our k is equal to the natural log of 1 over 1,000 divided by 24. Okay, so we have our k. Now we can plug everything in and solve for our time t. Solve for our a rather. Okay, so now we solve for the amount when t equals 16. Okay, so now we kind of separate that a little bit. We use the same formula, but our a is unknown because we only know what the new amount is at 24 hours. We never knew what it was at 16. So now we're solving for the new amount. A is equal to a sub 0. Again, it started at 100,000. E, we now know what k is. So it's natural log of 1 over 1,000 divided by 24 times our time, which is 16. Okay, so if we plug all that into the calculator, we'd end up with 1,000. So you have 1,000 bacteria after 16 hours. Okay, so that's why we couldn't just automatically plug in 16, because if we try using this formula, we were trying to solve for a new amount. We had our starting amount, and we had everything but our k. So we had to find a k first, and then we could plug it in. All right. So any questions on that one? All right. Actually, that is